Hello everyone, I'm Ryota Yasudo from Hiroshima University. In this video, I'd like to talk about adaptive bulk search, solving QUBO problems on multiple GPUs. First of all, I'd like to introduce QUBO. QUBO is an NP-hard problem of finding an n-bit vector X with the minimum energy. An input of QUBO is given by an n by n symmetric matrix W called a weight matrix. It can be represented like this. The objective of QUBO is to minimize the energy, defined by this formula. Given the weights, we search for an n-bit vector with the minimum energy. Let's say we are given an input shown here. The energy becomes the total value of the elements in this matrix. If an n-bit vector X is 1011, the energy is equal to -8. This is the sum of the elements highlighted in white in this figure. So why is QUBO important? This is because many NP problems can easily be converted to QUBO, and hence a QUBO solver is potentially a solver for a wide range of optimization problems. For example, maximum cut problems and traveling salesman problems can be mapped into a QUBO instance that is a weight matrix. Also, a QUBO instance can be equivalently converted to an Ising model, which has recently attracted attention in conjunction with quantum annealing. So, solving QUBO can be an alternative method to quantum annealing. This slide shows our main contributions. First, we propose the adaptive bulk search, ABS, a new search method for solving QUBO. It involves an efficient algorithm with O((1) cost for evaluating energy per solution. Second, we implement the ABS on multiple GPUs and show experimental results with max-cut TSP and random QUBO instances. The ABS attains more than 1 terasearch rate, which means that it can evaluate more than 1 trillion solutions per second. A local search would be a good heuristic method for solving QUBO. For an n-bit vector X, let us define flip k of X. It is a vector such that the kth bit of X is flipped. Let's say we are given X equal to 10110. By flipping X2 from 1 to 0, we obtain flip 2 of X. We can use this function for obtaining neighbor solutions. This figure illustrates a local search for QUBO. Let's say we now have 10110. Flipping each bit, we obtain 5 neighbor solutions. We can repeatedly search for the best solution like this. In a local search, we must evaluate the objective function. In the case of QUBO, it is the energy for n-bit vectors. Let's consider the computational cost for evaluating the energy. Naively, it is evaluated by computing this formula directly. From the formula, evaluating energy requires O of n squared cost. Every time a solution is moved in a local search, O of n squared cost is required. This cost can be reduced by incremental computation. Let's consider the difference of the energy denoted by delta k of X. For example, delta 2 of X is the energy of flip k of X minus the energy of X. Obviously, the smaller delta is better. Since the difference between X and flip k of X occurs only in Xk, we should compute the weights in one column and one row of a matrix. As a result, we can evaluate the energy with O of n cost by adding delta. Furthermore, we can use incremental computation for delta of x. Let's consider the difference of delta k after xi is flipped. Suppose that delta for all bits are stored in a memory as well as x. Now, how can we compute the difference of delta? If I is equal to k, we just reverse the number sign. If not, we just add or subtract two weights written in red in this example. Using this incremental computation, we can evaluate the energy of all neighbor solutions with O of n cost. It means that the computational cost is reduced to O of 1 per solution. When we store delta for all n bits, we can select a bit to be flipped from all of n bits based on energy. One simple selection policy would be a hill climbing. It selects the best one from all of n bits. It quickly finds a local minimum. However, once it finds that, hill climbing cannot escape from it, so it is difficult to obtain a global minimum. On the other hand, our selection policy selects the best one from a segment of the bits. So the ranking of the selected solution depends on the number of bits in the segment. Our selection policy is analogous to simulated annealing. If a segment is small, a bad solution is sometimes selected. It corresponds to high temperature. If a segment is large, good solution is always selected. It corresponds to low temperature. As a result, it can escape from local minima. This slide shows iterative steps of our selection policy. After we compare the value of delta in a segment, we find a bit with the minimum delta and flip it. In the following iterations, we repeat the same operations. Our selection policy has several advantages. First, costly random number generation such as CU_rand is not required. Second, a flipped bit is never reflipped in the following several iterations. In this example, these 4 bits are never flipped at the second iteration. In a hill climbing and simulated annealing, however, consecutive flips of the same bit may occur near a local minimum. Third, a bit flipping operation is always performed in every iteration, while in SA, a bit may not be flipped near a local minimum. Next, I'd like to talk about the adaptive bulk search, ABS. The concept of ABS is to perform a large number of local searches. ABS is cost efficient because it uses constant cost for evaluating energy. We attain full utilization of GPU computation resources. We can adapt any selection policy in a local search, so we can change heuristics according to a problem to be solved. In the ABS, local searches are performed repeatedly with genetic algorithm. A host has a solution pool and randomly selects 2 vectors from here. It performs a crossover and a mutation operations, and then GPUs perform a local search. A host and GPUs operate asynchronously, and hence, communication overhead is small. This slide illustrates an overview of the ABS. A host CPU manages a solution pool and performs genetic algorithm. Generated solutions by genetic algorithm are sent to a target buffer as target solutions. Each CUDA block in a GPU reads a target solution from a target buffer and performs a search in parallel from a target solution. After the search, the best found solutions are stored in a solution buffer and sent to a host. A host CPU and GPUs repeatedly perform these operations asynchronously. Detailed operations in each CUDA block are shown in this slide. It performs searches in iterative steps. Here we can see 3 iterations. In each iteration, it performs a local search from a target solution. In this case, O of n squared cost is necessary to evaluate the energy of the target solution because incremental computation is not possible. This would spoil the performance of the ABS. To avoid this bottleneck, we introduce a straight search. Let's say we now have a solution X and a target solution T. Before moving to T, we can search neighbor solutions such that a solution gets closer to T. In this example, we perform a local search with 4 iterations because the Hamming distance between X and T is 4. Because the Hamming distance is less than n, total costs are less than O of n squared. In this manner, we can perform a local search and move to a target solution at the same time. As shown in this slide, straight search is performed from the previous solution to the target solution in each iteration. Since the straight search evaluates the energy of vectors all the way to the target solution, it may find a better solution, while the computational cost is also reduced. Next, I'm going to show experimental results. We implemented the ABS on a system equipped with the Intel Core i9 CPU and 4 NVIDIA GeForce GPUs. This GPU has memories and computing resources shown here. We used QUBO and aimed at full utilization of computing resources. We evaluated the performance using 2 metrics, time to solution and search rate. The time to solution is the time to obtain good solutions. For example, the time to obtain best known solutions. The search rate is the number of energy evaluations per second. So it denotes the throughput of the system. We use 3 benchmarks for up to 32 kilobit QUBO problems. MaxCut, TSP, and randomly generated matrix instances are used. This slide shows the time to solution for MaxCut problems. Graphs are derived from gset. A graph with n nodes can be converted into an n-bit QUBO instance as shown here. For various graphs, including random and planar graphs, the ABS finds an approximate solution mostly within 1 second. This slide shows the time to solution for TSP. The problems are derived from TSP-lib. An NCT TSP can be converted into an n-1 square bit QUBO instance. While it seems more difficult than MaxCut, the ABS finds approximate solutions in a few seconds. This slide shows the time to solution of randomly generated matrix QUBO instances. Every weight is selected from all 16-bit integers uniformly at random. Since these problems are randomly generated, we obtain good solutions by repeating searches until the best solution converges, and we regard them best known solutions. The results show that the EBS quickly finds good solutions for problems, even with 32 kilobits. Next, we evaluate the search rate, that is, the number of energy evaluations per second. For 1 kilobit problems, the ABS attains more than 1 tera evaluations per second, which is 60 times faster than prior work. Also, we evaluate scalability when we increase the number of GPUs. Thanks to asynchronous operations of the ABS, the search rate is linearly improved as the number of GPUs increases. Finally, I'd like to conclude by making the following points. A QUBO solver is potentially a solver for a wide range of problems. Also, it can be an alternative method to quantum annealing. We have proposed Adaptive Bulk Search (ABS), a framework for solving QUBO problems. It involves efficient algorithm for evaluating energy. We combine a local search, a genetic algorithm, and a straight search. We have implemented the ABS on 4 GPUs, which supports 32 kilobit QUBO problems. The ABS finds approximate solutions for max-cut TSP and random QUBO problems. The ABS attains more than 1 tera search rate for 1 kilobit QUBO problems. That's all. Thank you for your attention.